Hey guys, we're here with lesson 3.4, Exploring Linear and Exponential Growth. So the opening here talks about a movie called Pay It Forward, where a little boy wanted to do good deeds for people, and then the people he did good deeds for, he wanted them to pay it forward. So if we look at this chart, let's assume that the good deeds occurred each month. Look at how quickly this exponential growth can grow. On month 1, if a person does 3 good deeds, then by the second month, there will be 9, the third month, 27, and on and on and on. But if the little boy, his name is Trevor, was the only one to perform these good deeds, you can look and see that it's increasing by 30 good deeds per month, right? But on month 5, the value is much smaller than it would be if we used an exponential function. So let's explore why. All right, we are going to just discuss the difference between linear functions and exponential functions. Okay, remember that linear functions have a constant rate of change. So the first example, Fabian is at the store picking up some groceries. He needs to get a gallon of milk and some apples. The gallon of milk costs $3.30 and apples are 35 cents each. The function f of x represents Fabian's expenses at the grocery store. Okay, so let's talk about what all these pieces mean. F of x represents the total cost of the apples and the milk. Okay, that's what our equation is equal to, f of x. What does 0.35 represent? Well, that represents the cost per apple. Each apple, right, 35 cents each for the apples. The x represents the number of apples that Fabian buys, and the 3.30 represents the cost of a gallon of milk. That is constant. Okay, so when we are using the slope and y-intercept here, we can create this linear function. In linear functions, remember, the slope always connects to the x variable. The y-intercept exists when the x is equal to 0. Okay, what will you pay even if you didn't buy any apples? Now, let's go ahead and take a look at example 2. James has been studying a type of mold that grows quickly. He has created the function f of x equals 200 times 1.20 raised to the x power. This is an exponential function. What does f of x represent? Okay, so in the linear function, f of x represented the total that we paid. In the exponential function, it's the number of mold spores that we have in a given week. So that's our total. Good. What does 200 represent? Well, in exponential functions, that is our principal amount or our starting amount or the y-intercept. So this means that we started with 200 spores of mold. What does the x represent? The x is our number of weeks. And 1.20, remember for exponential functions, we had those parentheses, 1 plus r. That is going to indicate that we have a growth rate of 20%. 1 plus 0.20 will give us 1.20. All right. Now let's compare linear and exponential functions. Inspired by the idea of doing good deeds, Tallulah has decided to do good deeds around her community. She has devised 2 separate plans and needs to pick the best one. Plan 1 will have Tallulah doing good deeds for 4 people each month. Plan 2 has people who have good deeds done for them doing 2 good deeds next month, so they're paying it forward. Okay, so here are our 2 equations. Plan 1 looks like it's linear. F of x equals 4x, and then we could say plus 0 here. Plan 2 looks like it's exponential because that x is up in my variable. It looks like Plan 1 is affecting more people than Plan 2. So as we go by each month, it looks like Plan 1 is affecting more people than Plan 2. But what happens in the 4th and 5th months? This is the key here, okay? In the first plan, this is a linear plan, okay, which means it has a constant rate of change. We are adding 4 good deeds to each month. So this next month, we will have 16, and 16 plus 4 will give us 20. With our exponential function, we are multiplying each good deed by 2 every month. So we're multiplying by 2, multiply by 2, multiply by 2. In month 4, we're at the exact same amount of good deeds, but if I multiply that number by 2, in month 5, we begin to exceed or go over or have more good deeds. So that is telling us something very, very, very important. Okay, an exponential growth function will always exceed a linear function eventually. As the x values continue to get larger, the rate of change for the exponential functions continues to increase, while the linear functions' rate of change is constant. Okay, and that's the main key here. Okay, let's take a look at the work here. And we can find the average rate of change for her plan from the first month to the 3rd month and from the 3rd month to the 5th month. So the work is done here, again, just using that rate of change formula, y2 minus y1 equals x2 minus x1. And as you do that, you can see the change here is the same, but over here, it's increasing. Okay, here are some practice problems. Again, I would go through a couple of them. As you do them, click on these little buttons and it gives you explanations for everything that you need. Then, when you're done with your practice problems, please review this little page at the very end of every lesson, and it tells you all the key points. For this lesson, the key point is that exponential functions will always grow or exceed linear functions. They may start off lower, but eventually they will become more. All right, go ahead and try out the quiz. Good luck.